Two things everyone believes about fine-tuning, and both are wrong. The first, that fine-tuning means retraining the whole model from scratch. The second, that you fine-tune to teach a model new facts. Forget both. Fine-tuning changes how a model behaves, not what it knows. And modern fine-tuning touches well under 1% of the weights. In fact, by the end of this video, you'll see how people fine-tune a 70 billion parameter model on a single GPU. Here is the one picture to hold on to the entire way through. On the left is the giant retrain model, a huge matrix of weights, locked, frozen. We don't touch it. Instead, off to the side, we add a tiny adapter, a small update that rides alongside the big matrix. Only that little adapter trains. The giant stays exactly as it was. That single move, freeze the giant, train something tiny, is the whole secret to making fine-tuning cheap. And it's the picture we'll come back to again and again. Let's build it up, one idea at a time. First, what does fine-tuning actually change? Fine-tuning changes behavior, not facts. Think tone of voice, output format, a narrow skill. You can make a model sound like your brand. You can make it always reply in clean, valid JSO. You can teach it to triage support tickets, exactly the way your team does. Notice what all three have in common. None of them is a fact you'd look up. They're patterns of behavior. So in every case, you're shaping how it answers. Its style, its shape, its habits. Not stuffing new information into it. That distinction is the thing most people get backwards. So hold on to it. So what about facts? If your facts change, today's prices, this week's documents, anything you need to cite, that is not a fine-tuning job. That is retrieval. That is RAG, where the model looks the answer up from an external store at the moment you ask. Behavior and style get baked into the weights. Changing facts get looked up. The single most common mistake in this whole area is fine-tuning a model to inject knowledge into it. Don't. Now, the old way of doing it and why it hurts. The original way is called full fine-tuning. You keep training the model and you let every single weight move. Watch the giant on the left wake up. The whole matrix lights up because all of it is changing at once. Billions of parameters all updating together. It absolutely works. And for a long time, it was the only option. But you pay for it in memory, in compute, and in time. Here's why updating everything hurts so much. To train a model, you don't just hold its weights in memory. You also hold the gradients and the optimizer state, which together needs several times the model's own size. So a model that's heavy to run becomes far heavier to train. On top of that, every task gives you a brand new full-size copy of the model to store. And there's a subtler danger. Push the model too hard on one narrow task, and it can override skills it already had. That's called catastrophic forgetting. So here's the idea that changed everything. LoRA. LoRA stands for Lorank adaptation, and it's beautifully simple. Take the pre-trained weights, call them W, and freeze them completely. You can see the lock right there on the giant. We will not touch it. Then, right beside it, we learn a small update built from two thin matrices, A and B. Their product is the update we add to W written. Delta W equals B times A. Look at the picture. Only that little adapter is glowing, because only the adapter is training. The giant W stays exactly as the pre-training left it, never moving a single weight. And because A and B are so thin, you end up training well under 1% of the model's parameters. The frozen base might be 70 billion weights. The adapter is a tiny fraction of a percent of that. Tiny to train, tiny to store. And here's the elegant part. Once you're done, you can fold that update straight back into W. So at inference time, the adapter adds zero extra latency. It simply merges in, and the model runs exactly as fast as before. But wait, why is something so tiny good enough? Here's the insight that makes LoRA work. The update you actually need, to adapt a model to a new behavior turns out to be low-dimensional. It doesn't fill the whole giant grid. It lives in just a few directions. So a thin A and a thin B squeeze through a small shared middle called the rank. Written as the letter R can capture almost all of it. And R is small, often just 8 or 16. That narrow waist between A and B is the whole reason the adapter is so tiny. Pick the rank, and you've picked the entire size of your adapter. And because each adapter is so small, often just a few megabytes, you can keep a whole collection of them and swap them in and out. One frozen base model, and a drawer full of little adapters, a legal voice, a casual support tone, a strict code reviewer. Load a different adapter, and the same underlying model takes on a completely different personality, instantly, with no retraining. The giant stays put. You just change the small piece riding on top. Now let's make it almost absurdly cheap. QLoRA. LoRa already shrinks what you train. QLoRA shrinks what you store. The idea: take that frozen base model and squeeze it down to just 4 bits per weight using a clever format. Call it NF4, normal float 4. That's tuned for how weights are actually distributed. So it takes up roughly 16 times less memory. You can see the giant coarsen into chunky 4-bit blocks. Then you train the LoRa adapter right on top of that compressed, frozen base. The giant becomes tiny in memory. The little adapter still does all the actual learning, in full precision. And here's the headline result. Fully fine-tuning a 65 billion parameter model needs over 780 gigabytes of memory. With QLoRA, that drops to under 48 gigabytes, small enough to fit on a single GPU. And the remarkable part is that you barely lose anything. The task quality comes out about the same as full 16-bit fine-tuning. That is how a model this enormous lands on hardware that one person can actually rent. So when should you actually reach for this? 3 tools and a clear order to try them in. First, just prompt the model. It's free, it's instant, and honestly it solves more than you'd expect. If that's not enough and you need facts that change, or sources you can cite, reach for RAG and look them up. And fine-tune when what you want is a way of answering, a behavior, a ton, a format. That prompting alone can't hold reliably. The clean test is this. If it's something you could look up, don't fine-tune it. If it's how the model should behave, fine-tuning is exactly the right tool. And now you know it costs almost nothing to do. One last thing, a few simple rules to do this well, so you get all the upside without quietly breaking your model. Let's put a real number on just how tiny that adapter is. Picture a 70 billion parameter model and watch the thin waist between A and B light up. That shared rank is 16. Add an adapter that's small to the attention matrices throughout the model, and you end up training on the order of tens of millions of weights. Set that against 70 billion, and it's roughly 1 weight in 1,000, about 1/10 of a single percent. Everything else, the whole locked giant, never moves. That is why these adapters are so cheap to keep around. Each one is a tiny slice of the model, small enough to store on disk and swap in whenever you need it. The giant carries all the knowledge. The little adapter just nudges its behavior. Now the data. It's tempting to think more is always better. But for fine-tuning, that's a trap. Remember, you're teaching a pattern of behavior. So every example you show, the model is effectively a vote for how it should answer. A few hundred examples that are clean, consistent, and all pulling in the same direction will shape that behavior beautifully. But pour in a million examples that contradict each other, with messy labels and mixed styles, and all you teach the model is to be inconsistent. So curate hard. A small, sharp, on-task set beats a huge, noisy one, almost every time, and it trains faster and cheaper too. One last caution. It is possible to overdo this. When a model is pushed too hard on one narrow task, it can start to lose abilities it used to have. That's the catastrophic forgetting we met earlier. Here's the quiet gift of LoRa though. Because the giant stays completely frozen, the lock never comes off. Its general knowledge is largely protected. And that's exactly why LoRa forgets far less than full fine-tuning does. But it isn't magic. Crank the rank up high and train too long on a thin slice of data. And even the adapter can drag the model off course. So keep the rank modest, keep your data clean, and stop early. Change the behavior with the smallest touch that works. So here's the whole thing in one breath. Freeze the giant. Train a tiny adapter beside it. Fine-tuning shapes behavior and style, never changing facts. Those belong to RAG. LoRA learns a small low-rank update, training under 1% of the weights and adding no latency once it's merged. And QLoRA quantizes the frozen base down to 4 bits. So even a 70 billion parameter model fits on a single GPU. The myth was that fine-tuning is huge and rewrites everything. The reality is a locked giant, and one small piece doing the learning. Fine-tuning was never about retraining the world. It's about changing behavior with the smallest possible touch. Subscribe for more such intuitive videos.